Okay. Hello, everyone. Thank you so much for joining us today for our final thesis presentation. Before I dive into the presentation, I'm wondering how many of you have sadly seen this picture before. Indeed, the more concerning question should be how many more we will still be seeing. Okay. Car accidents are a common issue that affects many of us, whether directly or indirectly. And statistically speaking, according to the World Health Organization, approximately 1.19 million people die each year as a result of car accidents. Also, car accidents cost most countries 3% of their GDP, and the car accidents are the leading cause of death for children and young adults. And what is even more concerning is that the primary cause of these accidents is not a mechanical failure or any external factor, but rather it's us, the humans. Studies show that 90% of car accidents fall under the category of accidents caused by human error. And due to this, a lot of technological advancements have been evolved over the past few years to eliminate the role of human when it comes to driving cars. This led to the development of autonomous driving, and autonomous vehicles or self-driving cars offer a promising solution to reduce the number of accidents caused by humans. Unfortunately, they still have their technical challenges and they need a lot of time for improvements. So now we are in front of two extremes and neither one of them is the perfect solution. This takes us to our project, which is a balanced approach between the two extremes, the fundamental human-driven cars, the traditional human-driven cars and the self-driving cars. It's designed to be a co-pilot, not a replacement, ensuring that the drivers are still engaged and the main decisions remain in their hands. With a standby system, we named it Brain Brake. Brain Brake is a brain-operated system for emergency braking and collision avoidance. It is developed by my colleagues Abdullah Ali, Ashraf, and Omar Hatem, Omar Sheta, Mohamed Ali, and me, Hashem. Under the supervision of Dr. Seif Eldawlatly and Dr. Ahmed Moro from Siemens, who we are blessed to be here today. Let me introduce you with a brief objective of our brain brake system. Our aim is to utilize the driver's brain signals to detect the need for braking ahead of time, faster than the human reaction. This system will then be embedded inside a car within the AutoSAR framework, an automotive standard. Here is a high-level view of our architecture, which our system Brain Brake takes as an input the brain signals and also takes the car's environment from car sensors, and it outputs a decision whether to brake or not, faster than we do, faster than the human reaction itself. Here is a small demo that demonstrates this criteria. Here is two cars. The lower one have our system Brain Brake, and the other one doesn't have. It have a normal driver. And what we aim to do is to drive faster than we do, is to brake faster than we do. Now I will leave the floor to my colleague Omar, who will tell us more about the project specifications.
Okay, so let me walk you through the specification for our system. So first of all, let me introduce to you the concept of inference time. Inference time is the time our system takes between having the input, then doing the processing, then having an output. So we need to have minimal time as possible. And our objective is to have less than 0.5 seconds, which is the average human response time. As in emergency situation, every millisecond count, and it can make the difference between a collision and a close call. To achieve this, we have hardware resources. First of all, we utilize embedded boards, and embedded boards are small computers that are designed to achieve a specific task. So we have a powerful embedded board that can handle the intensively computational tasks like handling computer vision and the brain signals. Also, we must ensure minimal communication delay as we have many components in the car and we need to deliver fast every signal to every component of the car. Also, our system is AutoSAR compliant, which means, and AutoSAR is a global standard for automotive software architecture. And that means that our system can be easily adopted by the automotive industry. Okay, this is the initial design. This is the design for our system. At the left, we have the brain signals acquired using headset. Then these signals is passed to the braking intention detection model, where we do some signal pre-processing and clean the signal. Simultaneously, we capture the environment using 2 cameras mounted on the windshield. Then it's passed to the object detection and distance estimation model, where we detect different obstacles on the road, and we calculate the distance between the driver and the obstacles. Then these outputs are passed to the communicator controller, which are distance and speed using SPI communication. Then the communicator controller, which is responsible for directing different messages to different components of the car, passes the output using the CAN bus to the braking electronic control unit, which then commands the car or do the braking action. And now Abdullah will continue on with the simulator.
Thank you, Omar. So now, as Omar and Hashem mentioned, we capture the surrounding of the car using 2 cameras mounted on the shield. However, it doesn't make sense to use a real car to test our system. That's why we are using a simulator. We are using Carla, which is a car simulator, to simulate a sudden braking event. This sudden braking event is created through asking the drivers to follow a car. This car brakes at sudden times. The driver has to follow the car without hitting it. Now let's dive deeper into the driving experience. Okay, so the driver controls the car using a Logitech G29 kit. We chose this kit because it comes with pedals. It has a full range wheel rotation, and it has adjustable wheel roughness. When it comes to the route itself, the trip takes place in a town-like map where you have straight roads and turns as well to diversify braking situations. The trip takes around 15 minutes with 40 braking events, which is around 22 seconds between each braking event. Now, let's take a look at some experiment. So, as you can see, the driving kit is mounted on a table. In front of that table, you have the computer that runs the simulator. The driver follows the car and brakes when needed. Now, you might notice the headset that the driver is wearing. This headset acquires the brain activity of the driver, also known as EEG signals. Now, I'll leave the floor to my friend Omar, who will tell us more about the EEG signals.
Thank you, Taha. So now we'll talk about the brain part in brain brake. So our goal is to use brain signals to detect your braking intention. But how does it even work? So our brains produce electrical signals to coordinate all their brain activity. And different areas in the brain correspond to different regions of decision making. So our goal is to read these electrical signals through conducting plates and try to find where your braking intention is and use it to brake the car. So to do this, we use what we call an EEG headset. EEG stands for electroencephalography, where we read the electrical signals coming out of your brain from different areas for different decision-making parts. As you can see, the small caps written here are the electrodes for different areas in your brain. And you basically wear this headset while you're driving in order to react at data. And this specific headset is called the Unicorn Hybrid Black. So these are the 8 electrodes present in our headset, and they're basically used to put different areas of the brain and try to record their activity. But in reality, data set that comes for us from EEG is not usually clean. Motion, noise, and other factors actually make the data itself not clean. And our goal is to use filtration in order to make it clean. So the first filter we use is the notch filter, which removes specific frequencies. So as you can see here, the smallest frequency is now removed. Next, we apply a bandpass filter, which is used to remove a range of frequencies. So now we have a much cleaner waveform that we can analyze and maybe get from it the braking intention. However, a third issue that arises is that EEG is very susceptible to motion. So if you move your head in any certain manner, this could cause a motion artifact to appear in all the signals. So we would apply what is called a common average reference or CAR filter to remove any average data set along all the electrodes to get for each electrode its unique brain signature and try to determine from it the braking action. So once we do so, we now have our data that we can put to our models. So we collect a window of the EEG data and pass it into our AI model. And we either get, okay, you can proceed, or not, and you need to brake. So now, important to notice how the process itself is created. You have a person who will move to the experiment that Taha has just explained. And after moving this with experiment, we will produce some EEG signals that we can analyze. We will do our process that we just mentioned in order to actually get a clean data set that we can use. And then this is used to create an AI model. It's very important to know that actually every person has his own unique brain signature. So this process is actually done for every individual. So as you can see, we have here 2 different individuals, and they produce 2 different waveforms. We apply the same process and get 2 different AI models. Now, an AI model is just not used offline, but actually real-time while you're driving. So the actual process is that while you're driving, you are producing your EEG signals, which we are reading, and then they are applied into our AI model. The AI model will then give a continuous decision of whether to brake and not to brake at certain instances. These decisions are then outputted into our computer vision module to actually decide how to brake. So we already decided that we should brake, but now how? The final thing I want to talk about is our architecture. So we surveyed a variety of different machine learning models, and we found the most suitable one for our experiment was extreme gradient boosting, or XGBoost. Very simply, you take the data that you have produced throughout your experiments, and you split them into subsets and train different AI models on them, taking their collective decision as your best. And once you do so, you can have actually a decision that we can input to the computer vision module. And now I'll let my colleague Khalid to talk about the computer vision aspect.
Okay, thank you very much, Omar. Now, moving to the object detection and distance estimation model. This model is responsible for taking the surroundings of the car and then giving useful information for the rest of the hardware system to actually brake the system in a timely manner. So now, our model is broken into 3 different functionalities. The first one is actually the object detection. For this functionality, you've used YOLO, which stands for You Only Look Once, which is a real-time object detection model that not only detects or identifies, it actually locates the objects on our frame. As you can see here, it shows the cars, and we've used this model as it's trained on scenarios that are relevant to our experiment, which is road experiments. And it can detect cars in a very speedy and accurate way. And we've used YOLO version 4 Tiny for its accuracy and compatibility with the hardware systems. Now, moving on to detecting the distance between the driver and the near obstacles. For this, we've used a technique named the stereo vision, where we mount 2 cameras at different angles looking forward on the windshield. And as you can see here, you can find the car onto the right, and we need to find its distance. So we calculate the disparity or the difference between the pixels or the corresponding pixels between the 2 frames, and we merge them into what's known as the depth map or the disparity map. As you can see here, the car is highlighted above with estimated distance of 5 meters between the obstacle itself and ourselves. But one might ask, why do we need the distance itself? We can just detect on the case of detecting an object. We have done so as this is our first contribution to literature to ensure comfort and safety to the passengers. We have done so by following the 2 seconds rule, which is a standard enforced by most European countries, which dictates that drivers should leave a trailing distance that at least can be covered in 2 seconds between the driver and the obstacle ahead. So now, given any distance, we can calculate this. Given any speed, we can calculate the distance that will be covered in the following 2 seconds. And if this distance is less than the distance estimated by the previous functionalities, then we don't have to brake. And if it's equal to the distance or more than the distance estimated, then we actually have to brake. So this was not our final contribution to the literature. I will be leaving the floor now for Abdullah to discuss more contributions that we have done.
So thank you, Mohammed. So now let's talk about our embedded hardware. So now we have the EEG model and the vision model ready, and we need to deploy them on our boards. But why do we need boards? Deploying the systems on an embedded board is very critical to our system, since we are trying to emulate a situation like real cars, where you have limited computing resources. So let's take a step back. We have the models that run and output some signals. These signals are distance, speed, and braking intention. And we want to deliver these signals to the braking control. Now, to do this, we follow an architecture that is widely used in the automotive telematics industry. The architecture is a multiprocessor ECU, where you have an application processor that is the brain of the ECU, and you have a communication processor. In our system, we choose the NVIDIA Jetson TX2 as our brain, where the models will be run. We choose STM32 boards to simulate both the communication processor and the braking control. Now, we chose the Jetson board because it comes with the GPU on board, which provides us with 2.5 times speed up compared to the processor on the NVIDIA Jetson. Now we have the output of the model on the application processor, and we need to communicate it to the communication processor. To do this, we use SPI, Serial Peripheral Interface. It's a communication protocol that is used in communicating between processors. However, the Jetson doesn't come with SPI out of the box, so we simulate it using software. Now, the signals are on the communication processor, which runs AutoSAR. The COM modules packs these signals into a protocol data unit that the CAN driver then sends on the CAN bus. This frame is then unpacked on the braking controller, where the signals are then used to brake. We choose CAN because it's robust to noise and is widely used in the automotive industry. Now, this concludes our discussion of the system design, and now I leave the floor to my friend Ali to tell us about the result of this.
Okay, so thank you, Abdullah. So now, having hopefully understood how the system works and how it's structured, it's important for us to evaluate how it performs in actual real life. So in order to perform the evaluation, let's agree on some criteria that the system has to satisfy. First of all, it has to be correct. When I say correct, I mean it has to be able to infer the driver's decision to brake. Also, it has to be fast, because if it's not fast, then the system is basically not working, because why bother? So let's start with the correctness. Okay, so thankfully, we were able to obtain 19 participants conducting 19 experiments, some of whom are present today with us in the audience, and some of whom are over here. Of course, we obtained the informed consent using the IRB form, and this acted as our data set for the whole system. So moving on to evaluating Omar's model, which was the part where we predict your brain, where we try to understand, do you intend on braking or not? We achieved an 80% accuracy, which is a very good number. However, since we as humans naturally don't consult one expert, we resort to others. We use some other metrics, such as F1 and AUC. They scored almost identically. It's 80%, which is a very good and promising number. And also to ensure that these results were not like the byproduct of sheer luck, we performed cross-validation. And we got 75%, which is a very good number. Okay, so let's evaluate Mohammed's part, which is the computer vision model, where we try to estimate a distance from the current vehicle to the target vehicle. So as you can see on the x-axis is the actual distance to the lead vehicle from my vehicle to the target vehicle. And on the y-axis, you have the difference between our estimated distance and the actual distance. So let's see. As you see, there's a negative trend. which basically translates to if the car gets farther away from me, the harder it is for the model to estimate the distance, which makes sense. The farther something is away, the harder it is for you to estimate this. Let's take an example. So let's say when the car is 15 meters away from me, you'll notice that our model says there's an offset of negative 2.5. So if it's 15 meters, the model says, okay, it's 12.5 meters away. And this actually shows how cautious and good our model is because it takes the worst case scenario. If it's 15 meters away, it assumes that it's closer. So let's see a live demo. This is myself on the very left. So we have my trained model. It's working in real life, in real time, and we'll see whether or not it detects braking. On the very bottom right, my foot, it's on the gas pedal. And on the top right is the simulation, where I'm following the lead vehicle. Okay, so it takes a sudden turn. And as you can see, our system correctly identifies the braking intention as seen by this watermark, brain brake or system. And what's interesting is if you see my foot, it still hasn't left the gas pedal. So I still haven't performed braking. This just shows that our system actually works and it actually beats myself in this case. As you see, this is where I hit the... So bottom line is the system beat me when it came to performing braking. Okay, and these are the average experimental results that we got from performing such an experiment. Okay, so out of 65 braking events on average throughout the whole experiment, we were able to detect 60 out of 65 braking events, which is more than 93%, which is a very good number. And out of 35 non-braking events, we're able to classify 15 of them as braking, which highlights how conservative our model is. Okay, so now we've established how accurate the model is. Now, how about speed? Because this comprises the make it or break it for our project. So recall that we've agreed that the average human reaction time is 500 milliseconds or half a second. And then let's take an extreme case of Formula 1 drivers who are arguably the fastest in terms of reflexes and reaction times. They stand at about 290 or 300 milliseconds, quarter of a second. I'm sorry, a third. And then brain brake beats both of them. So as for our contributions, there are two. Basically, we aim to publish a research paper in Biocast, which is a reputable conference. It's set to take place later this year in China. Also, we're planning on open sourcing the data set because we faced a huge problem when during the first semester looking for a data set. So this hopefully would make a contribution to the research community. We'd like to thank our family, friends, participants, Dr. Ahmed Moro from Siemens, and Dr. Seif Eldawlatly, of course, our advisor.